What's up guys, Jay here, and today we're looking at the engineering principles behind why a football travels in a curved path. A combination of Bernoulli's theorem, the coanda effect, and Newton's third law all give an explanation to a force known as the Magnus force, which is the ultimate force, which means you can bend it like Beckham. And I'm curving the ball into the goal from the corner. This shows there must be a force acting midway through the air, otherwise it'd be an impossible shot. This Magnus force comes about from a spin, and I'm applying that spin by wrapping my foot around the ball, therefore increasing the contact time with the ball, and impulse spinning force would be equal to force times time, so increasing that time increases the spinning. Looking at this clip again, the red cone represents the wall, and as you can see it's actually just going wide, but then it curls back in to the goal, representing a free kick shot. When a football is kicked in this direction with a spin, there will be a force known as the Magnus force which pulls it in this direction. This will ultimately result in a curved projectile path of the football. Why is this? Well, we have to look into the fluid dynamics. That's the airflow flowing around the object, the football. So if we look at the airflow flowing over the top of the ball, it's going to be at a low velocity at this point because it is opposed by the angular velocity of the spinning football. So here we get low velocity. It's oppositely on the bottom here. They are both acting in the same direction, therefore we get a high velocity. Bernoulli tells us that in fluid flows, low velocity equals high pressure, and high velocity equals low pressure. Therefore, we have a pressure gradient, high pressure, low pressure. The ball will move into the lower pressure area. That's part of the Magnus force, that pressure differential. There's also something going on behind the ball that adds to the Magnus force. The coanda effect is the tendency of an airflow to follow the path of the object it's hitting. This direction. It is proportional to the velocity. So we can see here that when the airflow over the top of the ball, because it is a low velocity, the coanda effect will be minimalized, so it does not follow this curved path. Whereas here, where the velocity is high, the coanda effect will be maximized. What we have here is a net flow of air in that direction. Because the ball is pushing the air in this direction, the air will push the ball in an equal and opposite direction, also adding to this downwards Magnus force. This cylinder in a wind tunnel models a football being kicked with and without spin. It helps visualize the coanda effect. You can see, as it starts spinning clockwise, air is forced upwards, and Newton's third law states that the ball must be forced downwards because of this. Let's have a look at some pros whipping it in.
It had power, it had bend, it had accuracy. Watch this. Starts way wide of the goal. That's 2-3 yards wide and just clips the inside of the post. That is quite a magnificent free kick.
Thanks for watching this short video, lads. So, to summarise, combination of Bernoulli's theorem, coanda effect and Newton's third law all explain the Magnus effect.